So it's a great pleasure and honor for me and for all of us to have Professor Auroop Ganguly from the Northeastern University, USA, to deliver his talk today on physics-guided uncertainty quantification. Let me do the honor of introducing Professor Auroop. He's a professor at Northeastern University in Boston, Massachusetts, and a joint chief scientist at the Pacific Northwest National Laboratory in Richland, USA. His research interests encompass climate risks and infrastructural resilience with spatiotemporal machine learning and complex network science. Prior to Northeastern, Auroop has worked at the US DOE's Oak Ridge National Laboratory and at Oracle Corporation. He's a co-founder and the chief scientific advisor of RISQ, a Boston-based climate analytics company. Professor Ganguly is an ASC fellow and obtained a PhD from MIT. So thank you very much. As I said, it's a pleasure to have you with us here today. Over to you, Professor Ganguly.
Thank you very much, Arun. So it's a pleasure to be here. And I was planning a little bit of a different presentation, but for various reasons, what you'll see is a compilation of some presentations which I have had earlier. Hope you'll still enjoy it. At some point, I can talk about some more tailored topics. I'd ask for 15 seconds of your time, just a little bit of silence for some recent event that happened in our lab. Thank you so much. So I'll talk about two things. Broadly, I'll talk about complexity in Earth systems sciences and Earth systems engineering. That's one way to look at one grand challenge that we face as society, as human society, and that we face in different countries, including here in the US, in India, and across the world. So and in that context, I'll bring up complexity, and I'll also bring up certain tools, whether it's tools such as complex networks, whether it's tools such as machine learning. I'll just talk about them in that context, but I'll also talk about how these tools interact with simulations, modeling simulations, and our understanding of processes. So first of all, in terms of when we think about Earth system science, traditionally, if you look at the left here, that has been the traditional approach where we try to model mathematically the process as we see it. I mean, although statisticians and applied data scientists have worked for a long time in tandem with modelers in these areas, the field has been a little bit dominated by modeling, simulation, trying to understand the physics. And there was a reason why this is so. There's some physics that we do understand fairly well, such as Newtonian laws of motion, conservation of mass, conservation of momentum, conservation of energy, etc. And if you put all of those conservation equations on a rotating sphere, that's the Earth's surface, you do get several interesting things, and there's some physics that we do understand. So these would be the first principles-based physics. However, there's a lot of physics at various scales across these different systems, whether it's atmosphere, ocean, land, cryosphere, etc., which we do not understand. And those physics we try to parameterize. They are also embedded within these models. These parameters are often somewhat physically based, or as physically based as we make them, but these are not first principles based physics. So the other thing that has caught up some interest lately is this whole area of machine learning. Beyond, if there is something in machine learning beyond what is done in statistics, or to the extent there is, That's something that has caught up a lot of attention lately. As I was saying, statistics has always been embedded within these models, whether in terms of estimating some parameters, whether it's in terms of post-processing model outputs, etc. But the hope with machine learning, and this on the right, what you see is a perspective article in Nature and one of their figures. So in that article, which was focused on deep learning and process understanding in the context of data-driven science. So they're talking about, and this was a couple of years back now, 2019. So they're talking about four different applications, if you will, or adaptations of deep learning approaches in jointly with process understanding, which have started potentially to make a difference in earth sciences. And when I say earth sciences, in this case, I often mean climate variability and change, so global climate modeling, hydrologic modeling, those kind of things. So anyway, so here, the kind of things that they have talked about, so, methods in object classification have been helping, looking at climate model ensembles, trying to understand patterns in the context of hurricanes. Methods in super resolution computer vision have been helping in statistical downscaling and blending model simulations. Similarly, with video prediction and short-term forecasting and language translation and dynamic time series modeling. So the second example is one that came from our lab by one of my former students, Thomas Vandal, who is now a scientist at NASA. So the idea is that these are some approaches that are being tried with the hope that some major uncertainties and gaps that remain in our understanding in climate and earth system science. There's a lot we do understand, but there's a lot we do not, like any field of science. So hopefully machine learning can bring a breath of fresh air and help us resolve some of those. But what we have been seeing again and again is in these kind of fields that can only happen if we blend machine learning with physics models and all these other tools that exist out there. So some things from these model simulations can be done relatively simply, I would say, through the use of simple models. It's more in the discovery processes in terms of what kind of questions you ask. So looking at model simulations and trying to get insights about heat waves and cold spells is something that the community has been doing. By the way, as I go through these presentations, I will highlight most of our work. That's not because I think our work is, the only ones that needs to be highlighted, but only because I know more about our works. There's a whole community working in these areas. These two, for example, one of this lines of work, which was published in PNAS, actually looked at heat waves. And it found that heat waves can be both worse than what we previously thought, but also more uncertain and geographically more variable than what we previously thought. On the other hand, there was some other work that we did with cold spells, which was fairly counterintuitive insight at that time, which said that, well, cold spells will grow less frequent in a warmer world. But the ones that do occur may be as long-lasting and as prolonged as the ones that we have seen earlier or see now. That's an interesting insight that the extremes, both tails, both sides of the extremes, heat waves and cold snaps, one will exacerbate, one will persist, despite the overall trend in global warming. So we saw this across several of our papers, and then we looked at both of these through different kinds of indices, metrics, and then through extreme value theory. Extreme value theory, by the way, is one way to look at extremes, things like 100-year levels, things that are supposed to happen once in 100 years if conditions remain stationary. This is like saying that if conditions are statistically similar, then there is a 1/100 chance of some large event happening in any given year. Right, so that's the intuition behind that. And through that, we have found things both globally in terms of precipitation extremes that, what are 100-year events now will grow under what are often called business as usual scenarios might grow to 10, 12-year events, which has, by the way, major implications for civil engineering and electrical engineering and mechanical engineering design principles. So these are design curves, and these fundamental design curves we are seeing are already changing and could change drastically. That signal is clear at global scales, but by the time we come to regional scale, so we have done work in the US, in India, and also across different parts of the globe. I'm just showing one work in India, which was published in Nature Climate Change. There, the signals are not always as clear. So we do find signals, but we also see uncertainties, and we also see large amount of spatial variability. One thing to understand is that uncertainty in this case, when you see some sort of trend globally or across some aggregate scales, but then there's uncertainty at some other scales, uncertainty cuts both ways. If there is a trend combined with an uncertainty, it means, by the way, that you have to be very careful in your design, and you might have to consider, if not the worst case, certain kinds of worst cases, because all or most design and planning endeavors are often done with not with average cases. So designing with average is like designing a bridge with average traffic, or designing a building with average load. So that bridge will fail multiple times, right? So you always design with some sort of worst case, some sort of bad situation, maybe not the worst case, but as worse, and that is a risk balance trade-off. So an uncertainty factors into what that worst case might be. So it's very important to understand that. Some other things that we could also do with these climate models is look at these model simulations and build indices that matter. So, for example, one of our Nature paper in 2015 looked at climate variables, especially wind vectors that are generated from climate, and looked at what is called coastal upwelling. Coastal upwelling is a process that happens because of differential heating of land and ocean. And what it does is it moves water that's below the ocean up, and that is very important for coastal ecosystems because it replenishes the nutrient cycle. But if it grows too extreme, then what happens is that there's too much nutrient, too much flora and fauna. These are marine ecosystems try to flourish at the same time, and they cannot, and they kill off each other in some sense, roughly speaking. So we get dead zones. So there is an optimal in terms of coastal upwelling, and that's very important to be in that optimal window for coastal ecosystems to survive. And there have been various hypotheses that because of global warming, differential heating of land and sea, this coastal upwelling may intensify. And but nobody with data was able to show that. What we did is look at climate data, look at this index, and said that yes, there is support for this hypothesis, but also what is going to happen is latitudinally you'll see a spatial homogenization of coastal upwelling in addition to the intensification. Okay, so there are things we can find, like I was saying, despite the uncertainty, and uncertainty is very useful when we consider risk-based design, but there are things we can find in terms of these insights for heat waves, cold snaps, precipitation extremes, and coastal upwelling, just a few examples I gave. But in terms of the uncertainty, there are different types of uncertainty. So the uncertainties are sometimes large. So for certain variables, such as in this case, we are looking at precipitation minus evaporation. This is over the US, and this is with 3 US models. And the idea here is that if you look just at these top left, if you look at just these 6, then on the column you have different models. So think of these as if these are climate models with the same first principles based physics, but with different parameterizations. Think of this that way. So if some of you are familiar with the Lorentz system of equation, a very rough analogy is if you think of Lorentz equations with slightly different parameters like rho, beta, etc. and sigma. Slightly different, but still within the chaotic regime. So that would be these different models. And then if you look at the columns, if you look at the rows, these are different initial condition runs. So you have three different models, and this is NASA, NOAA, and NCAR, if I remember right, three models. And you can find more information in the citation. But then these are initial conditions. So think of these in the same way. If we go back to the imperfect analogy of Lorentz, these are initial conditions such as just as you have different initial conditions when you run Lorentz equation, except that remember when you run climate models, they are usually run as boundary value problems. This is not weather where you consider these as initial value problems. But despite it being so, and despite these differences being very small, so 10 to the power minus 14 kind of differences in the initializations in 1870, and the transient changes die out, but even after that, there are these huge differences that persist because of initial conditions. So this is very interesting. And as you might know, when there are different models, different parameterizations, slightly different physics-based approaches, if you will, you could think of these as, okay, as and when our knowledge increases, we will either converge towards model 1 or 2 or 3 kind of result, maybe. But for the initial condition runs, these are natural variability in the climate system. They may slightly, you may slightly have, as models improve, some people have said that you may slightly get improvements in some cases, but you'll really not get much improvement here. This is what it is. This is the natural variability of the system. This is chaos, or at least one part of, resembling chaos in various ways, where approximate knowledge of history is not an indicator of approximate, or cannot be used for approximate knowledge of the future, which works in many cases, which works in many standard statistical cases, but not when you have chaos. Now, beyond these six, if you look at these, which are shaded, these are just averages. So average of these two initial condition runs is here. Average of these three models for the same initial condition is here. And this is an average of all average. Now, if you look at these, and there is a color scheme here, wetter versus drier, etc. And this is just talking about precipitation minus evaporation 30 years later over a 10-year average compared to the 10-year average now. So if you look at that, right, then you see that this particular average of averages is sort of, is almost applying a smoothing. It's not as extreme as any of these, not as dry as this one, not as wet as that one. So then can we design for this average of averages? Well, that's again like saying, let's design for the average. Or in this case, we're talking about precipitation minus evaporation. The analogy would be that, over a 30-year period, 100 people will die from floods, 100 people will die from floods. So floods and droughts, so 100 minus 100, total people who die is 0. So that would be designing for this average of averages. And if you are comfortable with that, more power to you. But I'm not, and I'm sure most of you will not be. So we'll have to not just consider the average, we'll have to consider the range of behavior. And within that range of behavior, we'll have to consider the range that happens because of our lack of understanding of the system, which is what is happening across these models. This is different physically based parameterizations. Remember, the first principles physics is the same. Newtonian laws are the same, but it's the parameterizations. And then the natural variability of the system, at least part of which is caused by these small changes in initial conditions, things we are barely beginning to understand. And clearly it relates to complexity. Now you think, well, as these models improve, as we have better and better models, things will improve, right? Well, not necessarily, not always. Things improve often in fits and jumps. And we have seen over the last 2 cycles of the IPCC, these they are called CMIP 3, CMIP 5 climate models, generations of climate models. These are multiple suites of climate models. Going from CMIP 3 to CMIP 5 took 7 years, roughly speaking, but there was not much improvement in terms of stakeholder relevant variables at the scales at which stakeholders care about, such as for infrastructures, for urban sustainability, not that much improvement. So that's in terms of different modeling generations, improved parameterizations, not that much improvement. And in the latest generation of model, which is CMIP 6, which just have started, which have just come out, some are still coming out. There are significant uncertainties remain, let me put it that way, for example, in cloud physics and so on. Now, in addition to that, there is this large variability. Now, variability, of course, is not exactly equal to uncertainty, but in this context, this variability translates to uncertainty in projections in some ways. So this is temperature on the here, and this is precipitation, and this is global average from 1950 till 2100. And the idea is that as you look at global average, as you look at lower and lower resolutions, more aggregate scales, the uncertainties are often less. They tend to balance out, law of large numbers, if you will, or a variant of that. But even at that scale, look at precipitation, for example, there is significant variability. And then if you go to higher resolution, and this is that variability, the blue is the variability because of different models or lack of understanding of physics, and the orange is variability, which is the natural variability in the system. And you'll see that at city scales, so if you go from global land in temperature, even in temperature, US and Phoenix, just one city, look at how this natural variability starts to dominate. And the same, if you go for precipitation, it's even more, even at global scales, this variability is large. And this variability is something that's difficult to translate to likelihoods and difficult to do risk-based planning. Okay, so what do we do? Well, lots of things that people have said, of course, and lots of things that are happening in the physics, in the statistics, data-driven sciences, trying to understand that in the modeling. But one area that people have started to think about a lot these days, and all of us are waiting eagerly for significant breakthroughs to come in that area. It's still very early to say that we have had breakthroughs, by the way. That area is machine learning, data-driven sciences in some form. And there was the Department of Energy now has their own model, and they actually ran a call for white papers to address these areas. There are several white papers submitted. I'd urge you to take a look, one of which was ours, and this figure comes from there. So this talks about water in the Earth system. And on the left side, what I have is the different physical processes and how they are interconnected. So something like processes over oceans, such as El Nino. So climate oscillators, they're often called, which could be ocean-based, could be atmosphere-based also, but many of those are ocean-based. These have impacts on regional hydrology and regional water cycle, regional weather patterns. So these are called teleconnections. Something happening way over in the Eastern Pacific Ocean, such as El Nino, may impact, Indian monsoons, for example, even, and the flow of the interannual variability in the flow of the river Amazon, and the drought and flood cycle in the Sahel region of Africa, et cetera, et cetera. So these kind of things, ocean oscillators and how they impact regional land climate through what are called connection at longer spatial scales. Very important to understand. Many other processes, obviously, and I'm just giving a few examples here. I'll not talk through all of those, but all of these processes are important. And especially when you go, the atmospheric system remains incredibly challenging. One of the large sources of uncertainty in climate remains cloud physics. But then the uncertainties, when you go into the ground, it sort of becomes even higher because of the heterogeneity of hydrologic processes, because there are so few observations below the ground, etc. And then when you talk about the interconnections, so things like evaporation and things like that, it becomes incredibly hard. And what is harder, as I was saying, is if you try to go to higher and higher resolution, lower resolution, aggregate scales, you might say, well, law of large numbers, some things will balance out. That doesn't mean you understand everything right. But okay, things will balance out, uncertainties are often less, but as you try to go to higher and higher resolution, uncertainties dominate. And there's also, there's various other reasons. One thing is we may not understand the physics or the parameterizations at those scales very well. So those are two areas which I'll talk about a little bit more, these long-range teleconnections and going to higher resolution. By the way, all of these, based on all of these processes and our understanding or lack of understanding thereof, what we suggested, this is a large team. I mean, you should see our, I request you to look at all these white papers, but especially the ones, in this context, the one that we submitted with several co-authors. So, here what you're proposing is that Earth system models, these are global climate models now called Earth system models because there are so many components, needs to benefit from many different types of what could be called artificial intelligence approaches or machine learning approaches or broadly data-driven approaches. But it also needs a variety of test beds, some of which exist, some of which we have not accumulated in the right way yet, and we are gradually, we as in the community, we are gradually trying to do. And also needs different kinds of test beds, all the way from the very simple idealized Lorentz system that I was talking about to the so-called real climate models, the large climate models, but a variety of things in between, from primitive equations to simplified weather climate models. So we need a hierarchy of test beds to be able to do this. And this is not something that is not done at all. There are nascent work, I would say, that has started to do these things, including some fairly well-funded work. Couple of things here. One aspect of combining these data-driven sciences or artificial intelligence or machine learning with physics, which needs to be done here. We cannot just leave behind all the physics that we know and think that artificial intelligence will solve it. At the same time, we do not want to ignore the promise of artificial intelligence. And I'm using AI here very broadly. So some people would say, okay, there is complex network science. Network science, is it AI? Is certain kinds of computational statistics AI? Is machine learning, deep learning? I'm using a broad definition here to include all of those, right? So somebody else can look at the semantics of what should or should not be called there. But within that context, there are at least a couple of things when we combine physics and machine learning. Of course, there is extraction of causality because we don't know often enough of the physics, and hopefully from data, we might be able to infer some of the physics, or at least refine some of the physics we know. Then there is uncertainty assessment, and we have been talking about physics-guided uncertainty assessment for a while now in different contexts. But the other thing is when we talk about machine learning, one thing you could do is go inside the models, and then the machine learning helps develop or refine the parameters of the models themselves. So this is what we have been calling machine learning enhanced physics. And the other thing you can do is use machine learning to look at a lot of data sets, whether these data sets are from observations, remotely sensed observations. We've been working with NASA and other agencies, or whether these are from large-scale model simulations, such as those generated by NCAR, National Center for Atmospheric Research, NOAA, and a variety of groups now. I mean, India has a very, from the Indian Institute of Tropical Meteorology, there is an Earth system model there. So all of these results are archived. These are very complex models, require high performance computational power. You cannot just run them and throw them away, and you cannot run them arbitrarily. So these results are archived. So all of these models, simulated, observed, remote sensing data, leads to large, very large data sets. So this is real big data in the sense, but the kind of things that you want there are often small data. We often want to gather insights about extremes and rare events. So the kind of things there that we have different understanding of knowledge and processes and physics, some of which are already embedded in the models, but some are not. So question is, can we use these knowledge and processes to improve machine learning, whether it's through covariate selection, whether it's through application of constraints on the outputs or on the cost function, or whether it's through defining the architecture or the representation of the machine learning approach itself. So those are the kinds of things. I'll now quickly take you through some examples. So in the context of teleconnections, we have looked at from ocean-based indicators to flow of rivers across the world. And I have some citations here. For if you're interested, you can take a look. These kind of things use complex networks in climate. This was by now it's older work, which have been published, but recently there have been some significant, very good work across different groups, such as by the group of Jürgen Kurz in Potsdam, Germany, where they've used complex networks to get different kinds of predictive understanding about climate systems, especially about teleconnections. I was talking about these long-range dependence. One other thing is that sometimes these kind of systems or this understanding can help us get better insights, whether it's through covariate selection, whether it's through understanding certain processes which are interconnected across many different scales, and we can get insights about those from models and from observations. I'll not go into those right now, but I'd encourage you to look at these papers. Very fascinating area. We're actually getting better with data and these kind of tools in terms of understanding the science itself. And then in terms of going from lower resolutions, these models, Earth system models, climate models, many different models are often generated, were often initially formed to get better idea about long range things or aggregate level processes such as atmospheric dynamics. But more and more now we want to use these things to understand what climate change, for example, or changes in weather extremes would imply for scales that we care about, such as infrastructures, such as human institutions, such as communities, such as buildings, such as transportation sectors, electric grid, such as even cities. And as I was showing earlier, there's a lot of uncertainty there. So this is where some of us have been applying deep learning and various machine learning kind of approaches. The problem is one of function approximation, and the problem can be cast as computer vision. There is one map at lower resolution, another map at higher resolution, and you'd think that computer vision kind of approaches would work. However, some adaptations would be needed. So for example, uncertainties, as I was saying, if you intend to use these for risk-based planning, uncertainties are very big deals. And often these kind of systems do not look at uncertainty that well. They do sometimes, but not that well. So first of all, you have to look at uncertainty. Second thing is often they make very simplifying assumptions when they start to look at uncertainty, such as looking at, Gaussian process, data sets and assuming Gaussian distributions and so on. Some of those might need to be relaxed if we have to look at that. And the other thing is, as conditions change, will these kind of approaches, which are fairly complex, will these approaches be able to generalize to out of sample data? So those are the kind of things that needs to be checked. And uncertainty, especially in the context of skewed data, that's one thing we've been focusing on. And the other thing is, how well will that look in the future when conditions change? How well they might generalize? So this is in the context of deep learning. So that if that can be thought of as physics-guided machine learning, there is some physical insights that goes into design of those complex networks or deep learning methods. We've also just done a little bit of work in machine learning enhanced physics, where we looked at some different equations. This is not the standard Lorentz 63 model, but Lorentz 96 that's often used in climate models, and tried to see how different kinds of machine learning methods perform. And especially when you do these kind of things, basically we are competing with, or the community is competing with various kinds of data assimilation approaches. So we were looking at Gaussian processes and trying to see how they work in terms of uncertainty quantification relative to some other approaches such as random forest and deep learning and so on that has been tried. There's very much, people are just trying out various things. There's the hope, based on the hope that some of these things will improve these models. So that's the state in which we are in right now. Okay, so I talked about Earth system sciences. I talked about things that we understand. I talked about the gaps. I talked about uncertainties. This is a scientific presentation. Therefore, I'm talking a lot about uncertainties and gaps that needs to be addressed. This should not be confused with that we don't have any understanding whatsoever. We have significant amount of understanding of the basic physics, as I was saying, first principles based physics. So we have enough evidence for certain kinds of basic decisions. Yes, climate change is real. Yes, we need to do something about it. But then when we talk about what specifically do we need to do, in some cases we have a better understanding, such as heat waves and let's say public health impact related to heat waves. In some cases, that understanding is less and less. For example, when you go to droughts or when you go to cyclones, we do have some understanding, but it's not as much as you'd like it to be. And that's where some of these tools, methods need to come in. One of the largest uncertainties, as I was saying, is in the water cycle, all the way ranging from cloud physics to hydrology in the ground, to ocean dynamics that influence weather and hydrologic patterns regionally. Okay, now what do all of these things mean for engineering? This is taken from one of my recent presentations in KGML, Knowledge Guided Machine Learning, which was organized by Professor Vipin Kumar at Minnesota. I'll just cover this quickly, but I'd encourage you to take a look at that talk if you're more interested in the details of this. So even from a climate context, people talk about risk framework. Okay, so I talked about models and understanding the science. All of that science says that, okay, there is some natural variability in the system and some signal in the system, some of which is caused by anthropogenic or human-induced climate change. But this is an important aspect of disaster, but this is not the only thing. So these lead to weather and climate extreme events or weather and climate stresses. But unless they're combined with things like infrastructural vulnerability and societal exposure, they will not cause disasters. So that's why it's, or at least not catastrophic disasters. So catastrophic disasters are caused by a combination of three factors. Infrastructure fails, levees fails. You have the cyclone or the flooding or the drought, and then something fails. Your infrastructure systems, dams, levees, reservoirs fail. And you have exposure of lifeline systems such as transportation, power grid, or exposure of society. People, if you look at Katrina and New Orleans, some of the most vulnerable people living below sea level. If you look at Mumbai in India, some of the slums being at most vulnerable areas and most vulnerable to flooding, etc. So there is a need for disaster risk management, things that you need to do just before, during, and just after the disaster. But there's also need for longer term adaptation in terms of building your, your infrastructures or your exposures, reducing exposures in a way so that, you can adapt. And then there is what is called mitigation. This is greenhouse gas emissions changes in land use patterns, which can actually reduce the climate signal in the first place. So this is the overview of the climate risk framework, and this is from the IPCC. And this is IPCC uses standard risk-based approaches, but has framed this in the context of climate and natural hazards. And here, and remember I was talking about this comes from this presentation that I made for a workshop on KGML, very recent workshop, just a few days, couple of weeks, I think, back, or even less. KGML, or what they meant by that is knowledge-guided machine learning, as I was saying, physics-guided machine learning. It could be physics, it could be process understanding, etc. So broader term, they're using knowledge-guided. And here what I was saying is within this broad risk framework, there are so many things that you could improve if you think of, for example, flooding. So if you just focus on flooding disasters, which is a big deal, of course, across the world, there are so many things you could improve. We could improve knowledge-guided machine learning, could improve our understanding of the science so that, we understand these things better, to extract hydrological, and meteorological extremes from climate models. Knowledge-guided machine learning could help in terms of designing better infrastructure. So our understanding of design curves, which can help in designing protective infrastructure such as levees, dams, etc. Then beyond that, in terms of the disaster risk management itself, knowledge-guided machine learning can help in various things. One example being short-term quantitative precipitation forecast. Now, precipitation forecast at short-term, minutes to days, maybe, this is not climate scale in some sense. But the idea is that if we are thinking that climate change or variability might intensify precipitation extremes in different parts of the world in different ways, and those might lead eventually to flood disasters in some part of the world based on infrastructure exposure, etc., then we might have to get better in terms of being able to develop predictive insights in terms of managing these disasters. And part of that management is to get better with short-term quantitative precipitation forecasting. So this is not climate scale, but this still fits within the broad climate risk management framework. And then we need to look at climate adaptation in the context of multiple sectors. And one sector that we have looked at is regional and urban transportation. So, and then here are some examples. I'd encourage you to take a look eventually. Here are some examples where various kinds of machine learning, statistical methods can help. And I was saying I'm using a very broad definition of artificial intelligence here, including machine learning, network science. In some cases, even specialized statistical tools, which have been used for a while, but where certain kinds of physics understanding can help, right, in the process. So extreme value analysis, but with physics-guided covariates. Bayesian deep learning, but with physics guidance. Graphical methods, such as those complex network methods-based teleconnections that I was mentioning, but with an understanding of physics at those scales. Similarly, hybrid physics and Bayesian deep learning for spatiotemporal prediction at shorter time scale. physics-guided Bayesian uncertainty quantification, which I was saying is very important for risk-based design. And then here, process-guided network science and optimization guided by engineering principles when you try to understand, in this case, transportation systems or other systems like power grids and communication or water and wastewater systems, or the combination of those. Flooding, by the way, and the example here is flooding, and some people say, oh, floods, we sort of have a high-level understanding now. Well, I'm not so sure about that. You know, this is July 2021, and this is Science Magazine news article there. They say Europe's deadly floods have left scientists stunned. And this is the kind of thing that happens across the world. And, you know, when I talk about this, some people say, you know, for example, if you talk about India or some other places of the world, often developing economies get most devastated. And some people say, oh, you know, the science there is not well developed. Not everybody says that, but some people say it like that. And then I say, well, wait a second. Here we're talking about West Europe and US and Japan and Singapore. So where is that science? These are the most developed nations. So it's just the science that we don't understand very well. And then, you know, there was this very recent article in Nature which talked about, you know, floods are getting worse and 10 times more people may be exposed. And they are talking about, you know, different change drivers, urbanization, flood mitigation infrastructure, dams, levees, etc., increasing settlement. So this talks about the driver, this talks about, you know, hazard, exposure, vulnerability, that those three elements of risk that I mentioned. But this paper did not consider many things, or left very many things as uncertain, including this whole connection with climate and also, you know, incomplete records and uncertainty in population, etc. But already found this very interesting insight. So floods remain very interesting. And, you know, when you take a look at them, you have to look from climate to water hydrology, remote sensing, and then into some into some sectors, such as, you know, in this case, we're looking at transportation sector. And it's important to understand, as we think about this, there are two types of infrastructure when you're talking about floods. One is the protective infrastructure, dams, levees, and another is the infrastructure that is impacted. So transportation lifelines, power grids, water distribution systems, communication systems, as I was talking about earlier. So, you know, and one other thing is, you know, I showed you this curve where, okay, you know, precipitation extremes are increasing, clear signal of change, especially at global scales. And if you look at observed data, these are, by the way, based on models, but if you look at observed data for the time period when you have observations, the observed trends are even worse than what models would suggest. But by the time we try to convert them, this is North America, so this is continental scale. We try to convert them into design curves, and people often use intensity, duration, frequency, or depth, duration, frequency. We see that the signal is not often as clear, and especially then when we try to go to city scales and so on, the signals are not very clear at all. However, one thing we could do is these large ensembles runs, these runs that are made for natural variability in climate, maybe we can creatively use them instead of just using them to understand the variability, the natural variability and the uncertainty, and hence translation to uncertainty. Maybe we could use them to get, you know, just use them as data sources to get better at estimating these 100-year or 30-year or T-year levels, which are design curves. So that's something we just started to explore. We've also looked at physics-guided uncertainty quantification in various ways. So typically in climate models, what is often done, and remember here you're talking about long-term future, what is often done is you do look at, for each model, you look at model skills, how well they perform with respect to observations, but then you also look at how these models perform with each other, because obviously in the future you don't have observations. So these are called balancing skills and consensus across models. How these models agree with each other, that's consensus, and skills as in how these models perform with the observations. One other thing, though, that we could do, and people have been doing that, but it needs a much more, we think it needs much more deeper understanding and much better systematic approaches, is try to balance skills and consensus with our understanding of the physics, such as, you know, there are various data-driven dependence structures that we know, precipitation extremes relating to temperature. There are various physics-based insights that we know, how these things relate to each other. Can some of those help us improve uncertainty quantification? And remember, uncertainty is not just a side story. Uncertainty in this context is the key. It's very important. we cannot design based on mean. We cannot design based on average traffic, as I was saying earlier, just as an example. So we have to understand the range of behavior. Once we understand that, we can assign, if we can assign likelihoods, we can do risk-based design. If we are dealing with deep uncertainty where we do not know, cannot assign likelihoods, we can still look at these uncertainties and get better, whether it's in the context of infrastructures, whether it's in the context of water stress from rising stream temperature and reduced net water availability and what that means for energy security. So different kinds of applications. And so that's at the climate scale. At the weather scale, as I was saying, there are lots of things that happen. People say, oh, we cannot improve, these models cannot improve, physics cannot improve, maybe it's observations. And then Google comes up with, oh, we have a data-driven physics-free approach. And this is great that Google is looking at these things, and maybe there is some benefit to looking at these things, especially at shorter forecast lead times. The problem is some of you who are aware of Google Flu, might know that we are a bit wary of physics-free or these kind of approaches because of various things. People have used different kinds of hybrid approaches, including us. We've used different kinds of hybrid approaches which balance physics with data-driven methods and try to compare these things in the context of short-term QPF, quantitative precipitation forecast. Remember, as I said, these are not so longer term. These are climate timescales. Climate is thought of as statistics of weather and hydrology, etc. So you could look at statistics as in mean, as in variability, as in extremes, but they are still statistics of the system, versus short-term prediction is weather scale, not climate, but you still need to get better at that in terms of overall risk management. So that's why we are looking at these, and each of these things have different approaches in which you can bring physics and data mining or broadly AI, machine learning, data-driven sciences together. And then one other issue that has come up again and again as we face these floods, especially in urban areas, is how the urban subway systems, transit systems, metro systems deal with these kind of things, right? And we have been looking at what we call resilience, robustness of such systems in terms of the functionality that they're supposed to provide and how to bring them up. So here is at regional scales, we have looked at Indian Railway Network, we have looked at US Airport Network, and in urban systems, we have looked at the City of London, and we have looked at Boston and compared these two. I'd encourage you to take a look at that. This is where complex networks, again, not used in the context of climate, but used in the context of infrastructures where these networks actually exist. And you use different knowledge of the topology of these networks as well as the dynamics that's happening within these networks to try to get better insights into robustness and recovery of these systems. Once we do the Earth System Sciences and Engineering, there are various societal benefits. So for example, our group has been working with Climate Ready Boston. This is at city scales. At global scales, this is an invited article that we did for the United Nations Association of the UK, looking at different aspects from risk to resilience to the maladaptation cycle. Even small cities such as here in the context of Brookline, Massachusetts, public health impacts of urban heat waves. And also it's very important to think of, to bring in the private sector into these areas. So just as in catastrophic risk management for disasters at some point 20, 25 years back, the private sector built natural catastrophe models. Now is probably the time to embed climate into these kind of things and start to think of both climate risk and climate and infrastructure resilience in the context of climate risk. And we have some patterns in this area. And in the first area, we have this company, as Arun was saying, RISQ Risk. I'd encourage you to take a look at their website, www.risk.io. So here are some of the websites and things like that. Thank you very much for your attention. I will, and I'm ready to take questions.
Thank you, Professor Ganguly, for that very insightful and I would say, a very deep physics-guided talk. It was really nice. You touched really on some very hot aspects, literally, and I'm sure the audience enjoyed your talk. We'll take some questions from the audience. I see a raised hand, and let me actually. Yeah, so we have a question from Ayapadas. Please go ahead, Ayapadas.
Thank you, sir. Thank you, Professor Auroop. It was a very Hello. Is there an
Yes,
echo?
please. No,
Yeah.
there's no echo, please.
Yeah. Uh, it was a very insightful presentation and it covered a lot of bases in such a short time. Okay, I'll just come to my question because see, let's say take about Indian coast. On the let's say the Konkan coast or somewhere, the floods has always been there as an incidence. So within your methodology, I believe this question I had raised even in yesterday's panel, Professor Arun might know, is that floods have always been there. So is there a way to also encapsulate the historical methods through which this have been mitigated at some level or the other, with all the urban planning and the other taken into account? I know it is a very difficult task and a very difficult question but we always see the framework of 10 years, 20 years kind of framework, but the floods have been happening for 50 years, 100 years, to even 2000 years. So perhaps with machine learning, there is also some knowledge from those things which could be encapsulated in one form or the other. That is my primary question. And just a comment. Sir, in one of your slides, you mentioned when you displayed the equations, I think it was the hydrological equation. So that mu term was missing. So I might be wrong. So you were discussing about the environmental as well as the climate effect. So I was a little confused. So probably it was just a hydrological equation. It was Euler equation. Just a comment. That's all.
Okay. So to your 3 points, first of all, you are right. I covered a lot of things in short time, partly because it's a conglomeration of different presentations. I was hoping to make it a bit more tailored to this, but it didn't work out for various recent events. But I was still hoping to give a little bit of, there are few people who understand or know or know about all the complexities and all the research that needs to be done in these areas. And it's extremely important to try and understand that, and especially for for an audience such as at IIT Madras and elsewhere, that we always I'll just have my own rant here a little bit. We always go after these the Googles and the Amazons and do social media and trying to do better in terms of online marketing. Can I do 1% better, 0.01% better in terms of enabling somebody to online marketing better? And that's all fine. There's nothing wrong with it's great if you sort of doing that if it makes money. I mean, if someone makes money and then that's all great. No issues with that. But at least some of us, at least some of you, I would say, will have to take these global challenges, these societal priorities, national challenges, global challenges at regional scales, Konkan coasts, whatever it is, very seriously. And use similar kind of approaches, but in new ways. So it's not enough to say I'll use machine learning. Use machine learning for what? It becomes a standard hammer and nail problem. I have a hammer, therefore everything looks like a nail. So you need to go a little bit more into that, and we need more people to understand these, and that's why take a look. I mean, this is not just to you, but to all of you here, or anybody who will look here. I have various citations scattered here. Unfortunately, many of them are our citations only because I know more about them and can talk about them. But if you start with those, if you start with other things, you can look at very different citations. There are communities working in those. But as I was saying, a lot of uncertainties and challenges remain. So we have to look at that in much more detail. Okay, so that's one thing. I mean, yes, it's a lot of condensed material in short time, but hopefully it'll give you an initial, all of you an initial, or some of you an initial understanding. Second thing, in terms of the equation, I'll definitely take a look. This call will be recorded. You'll see those slides, and then just please let me know which slide, and obviously I'll thank you very much for pointing that out. I don't know yet which one it is, but we can discuss that offline. Your other point, which you said is the most difficult question about use of historical mitigation. One answer is easy. It's a short one-word answer. The answer is yes. We need to look at all of them. It'll be useful, by the way. I mean, we could have a discussion around this. I'm a chief specialty editor for a section of Frontiers in Water. The specialty is called Water and Built Infrastructures. We wrote an editorial article there for that. I mean, Frontiers calls it Specialty Grand Challenge. Take a look at that. I have cited it somewhere. It's me and Ruth Linnea Cahill.
Okay.
And it is about these kind of things. Historically, how we have managed this, what we do now. So one thing is, first of all, there are three aspects, I would say, just to summarize. One is that we definitely cannot ignore history, and not all the things are change. Some things have been happening. Floods have been happening, cyclones have been happening. So, and yes, people have been dealing with that. And are we always getting better? Not necessarily. So definitely, I mean, not always. Hopefully we are getting better in many different areas, but not always. We definitely have to take a look at what has been done. And that was one of the points I made in that earlier article as well. Second thing though, remember, things are changing. Things are not static. So the same flood or the same cyclone, if it happens today as opposed to 100 years earlier, would not hit with the same ferocity in terms of the damage it can cause, because there are more concentrated people somewhere. There are more certain kinds of infrastructure, all kinds of things. There are assets concentrated in some places. So things are changing that way in terms of what the exposure and vulnerability. Then also things are changing in terms of the hazard itself. And it's because of greenhouse gas induced climate change. Yes, global climate change, but it's also because of regional changes, agriculture, irrigation, right? Different kinds of regional changes have caused these changes. And in that context, again, it's great if we learn lessons from history. The Mayan civilization was destroyed because some people say that it was human-caused drought. Not the same kind of climate change we're talking about here of greenhouse gas emissions, but different human-caused regional climate change. The Indus Valley civilization, some people have hypothesized, gradually faded and people started moving elsewhere because of
Climate change.
geomorphology and climate change. This was not anthropogenic climate change as we talk about now, but this was almost natural climate change. And some people have called the Indus Valley civilization Goldilocks civilization because there was a window. It was a large window, several thousand years, when conditions were right in terms of both climate and hydrologic and geomorphologic conditions. So yes, people have adapted, and we need to understand, but you also need to understand that both the kind of destructions that these can cause, the reasons for these kind of events, and the infrastructure vulnerability, and the tools that we have at our disposal. All of these things have changed, right? So we need to be aware of those, and then yes, we do need to consider historical patterns. The other thing I would like to say is, and I don't know how much time I have, so Arun, please stop me at some point.
No. You have all the time that you need.
Okay. I mean, as you know, we are professors, so we love to talk and give us
no issues. And I wanted to let you know that there is one question waiting for you in the chat window.
Okay. So
and if you want me to read it out, I can do that. But if you're able to see,
let me just say this one thing in response to this, and I mean the broader response, and then I can take that one if I have a little bit of time. So yeah, so one thing that maybe many of you or some of you have seen that movie. What is it called? Oh My God, or no, I forget. It was a movie by Paresh Rawal. I think.
Yeah, I guess. Oh my God.
Oh my God, right? Yes.
Yeah.
So they were saying that insurance companies often say, oh, it's an act of God, therefore nothing can be done. Now, what I'm saying here has nothing to do with belief in God or not. I mean, that is fine. That is individual. All I'm saying is that certain things we can, as humans, we are responsible, right? And we cannot just blame somebody else, a higher power. Just as we cannot do that, and people have done that, right? In insurance, in other things. So what can we do? It's an act of God. The fact that we did not design our systems right, the fact that we have been emitting greenhouse gases, all the way from there, we have been not maintaining our infrastructures. I mean, we have left our most vulnerable people in the most highly exposed areas. Those things are certainly not important, and it's just this one God who needs to be blamed. And I've been saying that, okay, spare her a little bit, spare our gods a little bit, right? But the other thing is also a little bit dangerous if we try to attribute everything to greenhouse gas induced climate change, and now climate becomes the new god. Climate change is important, it's urgent, it needs to be dealt with, but we cannot say that this is, oh, we cannot do anything, this is global climate change, and unless people act in accordance with Paris agreements, floods will happen. No, we can do something in terms of our infrastructures, flood insurance, incentives, right, exposure, urban planning. So I hope that gives you an answer a little bit, right?
Yeah. Thank you, sir. I mean, my point, just to clarify, I don't want to proceed the discussion as such, maybe some other time. I was not
Very
even
good question.
mentioning that you need to take historical data as it is as a given. I was telling that even in the current system, can't it be factored at some zeroth level, first level thing when you have this machine learning thing? That's all.
Yeah, no, it is done. It is done to some extent, and it is, I mean, you should look at, there's somebody, Bert DeVries, VRIES, who has been, just as an example, and I talked about him because he's a granddad of my co-author, Ruth Linnea Cahill, with whom I wrote that specialty grand challenge is talking about. So he has been working he was working in Jordan, exactly doing this thing, balancing age-old architecture, age-old systems and ways in which people have managed various things, water cycles and dealing with water with, the challenges and solutions of this day. And there are various others who have done this. Upamanu Lal comes to mind from Columbia University. He did some excellent work in Africa along those lines. So that is considered, and not just zeroth order. That's interesting. As long as there is this also understanding that the nature of the problems, nature of the causes, the reasons, and the impacts, everything has changed. But so has, we also have better solutions now, hopefully. But
Yes.
Good question, very good question. Arun, I think you said there was one other question.
Yeah. Would you like me to read it out, or are you able to see it in the chat window?
Let me see 1 second. Okay. So I would like to know the reasons why physics-based ML models might not be preferred. Doesn't adding physics reduce the search space with more constraints leading to faster? No. So if I am understanding this question right, and again, this is the question seems to ask, I would like to know the reason why physics-based machine learning models might not be preferred. So I don't think that's the case. Nobody is saying that we should not do physics-based machine learning. It's more a matter of, do we have enough physics? Do we have a systematic way to bring physics into machine learning? How to do that? So that's what we are struggling with. And, you have to realize that when you think machine learning and artificial intelligence, we think, oh, everybody's working in it. But that's not really true. There are only few people who can really have the understanding, or some people do hands-on work. Some people, have broader understanding to guide the work. Some people have the understanding in their domains to be able to use the work. All of them are important. But even if you look at all of them, it's really a very small community. And then when you think about that community who also understands physics of something, and especially with something like Earth System Sciences, which itself is not easy to understand that physics, there are very few people who understand both things. So that's in terms of people. And then trying to build systematic approaches so that physics can benefit machine learning models. It is not easy. And I would submit, and it's not just me, I've talked with many machine learning and AI, data mining, etc. professors. It's probably much more difficult, orders of magnitude more difficult than making some incremental changes in, how Amazon or whoever, I don't want to name one company, although I already did, but any company does their online business, and I've done 0.01% incremental improvement. Because there is no physics. There is almost no baseline to compare with. You just improve something, it works for a while there, you have it, and then suddenly it changes. You didn't improve any understanding fundamentally. It just worked for a while, that's it. And then you change your algorithm. But here there is a physics. There are statisticians who have worked on it, and you have to improve this in a way so that it improves generalizably with out of sample data. So these kind of things, not just climate and earth sciences, but in various fields of sciences and engineering, is incredibly hard. And there are very few people who understand all of these sides to be able to do that. So to answer your question, you are right. It could potentially reduce the search space, and it could add meaningful constraints, physically relevant constraints, right? Such as conservation laws. So all of those are important. I think at some level people understand that. I have not seen too many people dispute the fact that it should be done if we can do it. Question is, can we do it right? How can we do it? Those are the kind of things that people are working on.
Yeah, great. I suppose Hari Prasad has answered the question. Yeah, so he has responded. I do not see any further raised hands in the audience, but I myself have a question.
Yes.
So there was one slide which had, a lot of Bayesian in it, and I do come from a data science background. So I'm just curious, in the context of climate science or Earth system science and so on, what does Bayesian mean and how does it get implemented? Can you give us some insights?
Very good
I
question.
can see you smiling.
Very good question. So there is nothing like Bayesian in the context of climate science, right? Climate science is agnostic to those things. Climate science would use that. Climate science per se is not,
Yeah,
these are tools and methods. So there is Bayesian in the context of statistics, of course, as you know, and there could be Bayesian in the context of machine learning, including deep learning. So if to the extent there's any of these tools are useful in climate science, then we can think of, okay, what does Bayesian mean, or if Bayesian theory or philosophy is useful. Now, I gave you two examples which I called Bayesian. One is in the context of what I was calling physics-guided uncertainty quantification. That was a paper which was published, I think, last year in Scientific Reports. The first author is Evan Kodra, Kodra, and I have that citation here, and Udit was deeply involved also. So what that does is it looks at climate model simulations and looks at skills and consensus, meaning how these models perform with observations in the period where both model simulations and observations are available, and then how these models perform with respect to each other in historical time as well as in future time. So skills and consensus. But then it also tries to look at physics guided, the physics that we understand. So certain relations. So precipitation extremes, if that's our variable of interest, in that case it was, how do those relate to temperature, which might be somewhat better predicted, right? So we try to balance all those things. There, the Bayesian is closer to traditional Bayesian. Bayesian statistics, as you think, is very traditional, and I would encourage all of everybody here to take a look at that. If you do take a look at that, please don't just read the paper, but also read the online supplement, because most of the fun stuff is hidden. And you'll know, this is standard Bayesian with priors, with posteriors, the usual way you think Bayesian. Okay. Then when you think about machine learning, deep learning Bayesian, that's the way people in machine learning they have their variant of Bayesian deep learning. They call it Bayesian deep learning. This is basically,
I was curious about that, right?
Yeah, this is basically a dropout strategy. So this is basically saying, okay, let's say you have, I'm just giving a very rough insight here. You have your neural network, which is all trained and such. And then you say, okay, I have this, but how do I generate uncertainties with that? What kind of things it could do? So you randomly do certain experiments. You randomly maybe take out some nodes. And how well do these perform, right? So these are called, dropout kind of things. Some people have, previously some people tried other things like, perturbing the inputs or the outputs, or perturbing the
the previous talk, in fact, talked about that, edge perturbation, node perturbation.
Yes. So, and the dropout strategy particularly, and this is, people like Yarin Gal, Gal, Yarin Gal and others, and, his old advisor, Zubin Gaharamani. So they initiated this, and many other people have been doing this. They have been calling this Bayesian deep learning, right? And it has an intuitive connection. It's not the standard Bayesian as we understand.
Okay.
That's probably an initial rough answer.
But would it also have, other manifestations or other implications? In the sense, does the word Bayesian imply other things in other areas, or are these the only two things?
No.
One is the standard one.
Many areas. So in general, statistics and data science methods are embedded within many aspects of climate. climate science and earth science and geoscience broadly speaking, and many aspects of science and engineering areas. So all the areas in which you think Bayesian, this can apply, right? It's just that and again there is this example, like I was saying, physics guided uncertainty quantification. That example that I was giving, where Bayesian is used in a traditional Bayesian sense. Method may be this or that. It can be improved. You may like it, you may not like it, but it's Bayesian in the traditional sense. It's just that I was giving this example of Bayesian deep learning, where it is called Bayesian, but it's something
Not
that means
in the
something specific. Yeah, it means something specific in that context. You buy it or not, but that's how it's used in that context.
So just one last question, at least from my side. Now, whether it is uncertainty quantification, or particularly if you're looking at forecasting either extreme events or even the regular forecasting that you do.
Yeah.
Let's say I do a forecasting, and then the event reveals itself, and then you obviously see some error. Typically, what are the modern ways of incorporating that prediction error back into your model?
Okay. So a couple of answers to that. If you're thinking weather scales, I talked about quantitative precipitation forecast, right? And these things needs to be improved in the overall risk management side of climate. Because if you're doing risk management, you have to do, if you're saying that you'll get more and more of these kind of hazards, you have to build your hazard, your disaster risk management approach is better, and part of that is the short term. This is not typically called climate in the climate science realm, because climate science is statistics of weather. That would be at least usually decadal to multi-decadal averages. Short-term precipitation forecasting or these kind of things are more weather.
Correct.
That being said, I personally think that broadly in the context of climate risk management, these do fall in. So let me first talk about that. In weather forecasting, there are various established ways to do that. So, and broadly speaking, there are different ways, but broadly speaking, I would say they fall under what is called data assimilation in some sense. So, similar to if, not just you, but I'm talking about the audience here, may have an intuition about, Kalman filtering. So data assimilation, as okay, you have your predictive model doing something, and then you hit an observation, and then you adjust, your variance covariance matrix, right? And then you say, okay, here is where I am, and then you move on from there. Similar kind of approaches, similar notionally. So actually, ensemble Kalman filters are used in weather and hydrologic prediction a lot, but there are other similar approaches, even basic nudging and things like that. There are various 3D VAR, 4D VAR variational methods that are used. That's in the context of weather. In the context of climate, it's harder. Still, data assimilation methods are used, machine learning methods are used. Are used is a strong word, are being tried, I would say, for improved parameterizations. But data assimilation methods have been used. But remember, in climate, we're talking about long-range forecasting. So we don't yet have the actual observations. And by the time the observations come, it's fairly late, because then we have to take 10-year average. So it's a while. So there, what we do is, we have to try and design systems and systematically evaluate these systems to see if we can, how well they'll do in out of sample data. So for example, we are talking about, in climate, we are often talking about non-stationarity. But if it is complete non-stationarity, we just cannot predict. So, but in climate, we're not talking about complete non-stationarity. So the weather in Boston will not become like the weather of Mars or Venus. Right. So, but it's constrained non-stationarity in the sense that weather in Boston may become something like the weather in North Carolina, which is in the south of Boston at some point 30 years later. Or in time, Boston may have seen El Nino events, which will grow more frequent with global warming. I'm just saying, it's in time and space, there could be analogs of what might happen in the future.
Absolutely.
Use those analogs to evaluate. And also
that's very interesting.
Build models. So those are the kind of things we have to explore for the longer time scale.
I think that the time and space analogs are really interesting. Very, very nice. Thank you. That was very insightful. At the moment, I don't see any. There is a question from Ashok. Let me actually unmute. Yeah, Ashok, please go ahead.
Thank you. Thank you for an interesting talk, Professor Ganguly.
I'm sorry, you're not audible enough. Can you please?
Yeah, can you hear me now?
Yes, yes, please.
Okay, thanks. Thanks for an interesting talk. Just a couple of brief questions. When you talked of ocean oscillators and teleconnections, are the oceans modeled as box models by any chance, or how is it? That was one question.
Okay.
And the second question on precipitation, do you also model convective precipitation? That's it.
Yeah. So ocean model is the large scale. I mean, okay. So first of all, when we think about ocean-based oscillators and teleconnections, not all of them have to be based on the kind of models you're talking about. So, I mean, one way to think of models is anything, right? It can be a data-driven model, it can be a physics-based model, it can be a parameterized model. So in that broad definition of model, yes, everything is model. But if you think of the physically inspired or physically motivated models, ocean-based oscillators, sometimes you can get insight from observations or from model simulations, right? By looking at various kinds of tools and methods, such as I was giving this example of complex networks. But to answer, I think what you're asking to answer that question, these are just ocean-based models from the Earth system models. So I would encourage you to look at Earth system models, such as the one from NCAR. It's CESM, Community Earth System Model, and the latest version is version 2. Or any other IPCC suite of models. These are called CMIP models, coupled modeling intercomparison project, and they have components for ocean and atmosphere and land, etc. Just look at the ocean model. It's grown much more complex beyond what it used to be. So I would encourage you to take a look, and then we can have a discussion on that. Regarding precipitation, do we consider convection? Again, in these big models, yes. And convection, as you might know, is one of the hardest things to deal with. But there are various parameterizations. We do not understand first principles based physics as well there, but there are various parameterizations to deal with that. In some of the other work that I showed, where you're looking at physics-driven, physics-based insights and things like that, there are various ways in which people have suggested looking at, let's say, temperature dependence of precipitation extremes. So one part of the dependence is as an atmospheric column, or even atmospheric columns across the world, as they get warmer, there is greater possibility of water that exists around to evaporate into the atmospheric column. So it's sort of like saying that as you get warmer, more water vapor can enter if that water vapor exists. So and when conditions are right, that water vapor can come down as rain. There is a mechanism that dictates it. This is called Clausius-Clapeyron. On an average, this holds. This does not hold everywhere because there are so many things. There are aerosols that are needed for these water vapor to form clouds. That water has to be there in that region. But on an average, if you look at many such atmospheric columns, you will see that, yes, this water vapor evaporates into the atmospheric column. So that's one thing. And they can come down as heavy rain if conditions are right. That is Clausius-Clapeyron. But convection also, because in a warmer environment, there's a chance that the convective cycle will intensify, as some people have said. Convection is like, you are very roughly speaking, you're sort of boiling water in some pot, and the thing that happens there, right? The cycle that happens there. So if your temperature is higher, if you're boiling, water at a higher temperature, that convective cycle will be larger. Just as that imperfect analogy, the same kind of thing will most likely happen. So convective systems will also, will potentially intensify in a warmer climate. So those kind of things people have looked at in various ways in trying to say what might then happen under different kinds of climate conditions, regionally and over time, etc. But yes, both in data-driven models, in physics-guided machine learning models these days, or physics-guided uncertainty models, and of course, in the physically inspired parameterized models, convective precipitation is considered, but it's one of the hardest things to consider. Does that answer your questions?
Ashok, do you want to respond?
Maybe he's mute.
Yeah, I think I need to unmute him. Yeah, let me just, yeah, 1 minute. Yeah, Ashok, would you like to respond?
Yeah, I was able to unmute myself. Yeah, thanks.
Yeah. Thanks.
Thanks for that. My specific interest on this was, I believe Neelan has some prediction on precipitation on the critical water vapor column. So I was wondering whether something further has been done on that since the paper came out some years back.
No, yes. So take a look at some work. I mean, we have done some work, but also take a look at the work by Paul O'Gorman at MIT.
Oh, I see. Thanks.
He's been doing some very interesting work. And then in Japan, there is this group, Sugiyama and others, so, who have done some interesting work. So there is a convective, there are people who have been working in convective, cloud convection and things like that. So if you're interested in the physics, I would encourage you to take a look at their work. And I'll be happy to point you to some of their lines of work.
And box model question was in the context of what Stommel had did years ago. So whether that is still being used is what I wanted to.
Again, if you think of that model, if you think of the Held-Suarez model in terms of the broader atmospheric kind of thing, I'm saying, often the newer the newer, much more complex models, they have a core, which is based on some of these things, but it's so it's hard to say it is that model, it's not that model. It's hard to say it is not that model because it's based on that. I'd encourage you to take a look at any of these big modeling groups, and especially NCAR, since NCAR is probably the most established, or at least one of the most established model. National Center for Atmospheric Research, their CESM, Community Earth System Model. There are different working groups. One of them is the ocean model. Take a look at that.
Okay, thanks.
So a lot of things there to understand. So I would not want to do injustice to that through a one-line answer, but take a look at that, and then we can discuss, or I can point you to somebody.
Thanks.
Sure.
So thank you very much. I think in the interest of time, we'll perhaps close the session now. Of course, participants are always encouraged to write to you in case they have questions and they couldn't ask here. On behalf of the workshop organizers, Professor Ganguly, it's been a great pleasure. It was a very, packed talk. We really traveled through a lot of topics, but the Q&A was also very insightful. So we really enjoyed it. And we, of course, look forward to more interactions and more talks. Thank you very much for making, as I said, making it to the presentation despite your situation. And of course, it must be daytime now for you, I suppose. So I should wish you a good day. And it's good night for a lot of participants here. With this, I think we'll draw this session to a close. And tomorrow, if you have a chance, please do attend Professor Ganguly whenever, depending on your situation. We have a good set of talks lined up, and we'll be honored by your presence.
Thank you.
And thank you very much. Thanks to all the participants and the speakers for the day for making yet another memorable day for the workshop. We'll meet again tomorrow at 3 o'clock. The day begins with a talk by Chandan. It's a tutorial talk. So see you all tomorrow. Tomorrow's day will be the final day of the workshop. But of course, as always, it is not the closing of the research. It's the beginning of research. Thank you very much. Shayan, would you like to say anything?
No, thanks. I mean, I would like to thank Professor Auroop Ganguly for this wonderful talk. And tomorrow we go on to the day 4 of this workshop with, we have 3 talks. There's a slight change in the schedule because of the unavailability of one of our speakers. So Professor Sunetra's talk is now scheduled at 7 p.m. instead of 8 p.m. So I just wanted to point that out. And so we meet again tomorrow.
Sounds like a flight rescheduling.
Yeah.
Okay, thank you very much, and good day and good night. We'll keep in touch.
Thank you.
Bye.